Okay, we should start. So the plan for today. That's oh, I forgot to take down the thing. I'm just so used to do. Today it's Cubist Advanced Cognitive Modeling. Okay, so if you remember, we got stuck midway through fitting a multi-level model that was giving bad behaviors. And today we're gonna unstuck the model, unstuck the chains, and make it work better. And to do so, we'll have to talk about reparameterization, which is a key notion in computational modeling. And then we will be moving into model comparison. If you downloaded the slides before, like exactly 5 minutes past 10, then re-download them because I've been changing them quite drastically in the last 15 minutes. And before we start, also, I would like to say there was a bit uncertainty about what's going to happen on the lecture for April 3rd, because I have to be at a conference. So we will have a guest lecture on Cognition in a Changing World, the Hierarchical Gaussian Filter by Peter Wade. Good. Are there questions that are hanging on over your head? Yes, I see that at least some of you are using the question and answers. I don't always get a sense whether you like the question, whether it clarifies. So it'd be nice if you just put an okay or something at the end after, if the answer is satisfactory. So I sort of get a feeling for whether the explanation worked or should I change something. Good. So back to the messy multi-level model. So if you remember, we were trying to fit this model, which is a memory model, where we have two parameters, a bias and an effect of memory. And each of these two parameters are specified at the level of the individual. That is, each individual has a specific bias. Each individual has a specific weight of memory. But these specific values are not independent from each other because they all belong to the same population. That is, in generative terms, each of the participants is sampled from an underlying population distribution. There is a distribution of biases and memory weights in the population, and each agent is an expression of that. Why are we doing that instead of estimating them separately? That's because that allows us to learn from other participants information that we can use to better infer the exact parameter value in these participants. What's the underlying reasoning behind that? Well, there's basically two big things. One is that as we get a participant to undergo an experimental setup, or we get in other ways observational data from a participant, right? It's never going to be infinite information. It's likely going to be only a handful of observations, which might make it hard to estimate with any precision the actual underlying parameter value of the participant. Second, we have noise in the generation of the data from the participant, right? That participant might have slept badly, right? That participant might have just won the lottery and be super enthusiastic or be falling in love, right? And that behavior on that specific day where we're collecting that data, right, might be deviating from the average behavior of that specific participant, right? So even if we had infinite data from that specific point in time, that data will not necessarily be fully representative of the underlying parameter value if we take them as the average, right, across a longer period, a trait of the individual in psychological technical terms. So by pooling the information that we get from those observations from that individual with the general picture that we get from all the other participants, we get a much more reliable picture of the parameters of the individual, right? We can drag away that individual if they were behaving in an extreme way from the outlierness of that specific day. Does that make sense? Good. So here was the code that we went through the other time. Just to remind you, right? We had to create a loop, not just by trial to generate the memory, but by agent, by trial, right? A nested loop. And when we then have the model, right, we have priors for the population level parameters, mean and standard deviation, and then for the specific parameters. So the vector of biases is drawn from a normal distribution with a mean of bias M here and a standard deviation of bias SD up here. Somebody on the Google Doc was asking, why are you putting 0.1, 0, 1, and 0, 0.3? You went very fast. You didn't explain. Fair enough. Why am I putting those values? Well, we've seen that, so bias is a parameter that normally would go from 0 to 1, your propensity to pick right in general. We work on a log-out scale, which means that we stretch it on a minus infinite plus infinite, with 0 being 0.5, exact random chance, right? So 50%, 50% of picking left and right. And a standard deviation of 1 brings us in a distribution that has the most of its probability density, right? The most probability of having a value between -2 and +2, which means between 12 and 87, something like that, 0.12 and 0.87, which is like the big bulk. And actually non-trivial probability to go all the way to -3 and +3, which really brings it close to 0 and 1, right? So what this distribution is doing is simply discouraging the idea that the population on average will always play left or always play right. What about the standard deviation? Well, we can plot it. Again, you should plot it, but a 0.3, what it's allowing me to do is basically to reach 0. So those values are drawn from the same reasoning that we had used when creating previous priors, right? We also had before a prior for theta that went from 0, mean of 0, and a standard deviation of 1. Right? And they should be sort of visualized and tested, and we'll do our prior and posterior update tests, blah, 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 right? Good questions on that. And then when we tell the model the likelihood function, right, we say that the choice for that trial, for that agent, is generated according to a theta, which is generated by having a bias for that specific agent plus a beta for that specific agent multiplied by the value of memory in that trial for that agent. If there's questions, ask them, right? Good. We run the model. We get both chains finished successfully. The mean chain execution time was 964 seconds, right? 15 minutes, about. The total execution time, meaning that one chain was much slower than the other, was 1129.5 seconds. It's not a big red flag, but it's telling us that one chain took about a bit less than 200 milliseconds more than the other. Milliseconds, seconds, which might be, it's telling you that the process was going on differently in the two chains, right? And then we get a warning. 2 out of 2 chains at an energy, blah, 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 less than 0.2. Go and read this page. We started looking at what might have gone on, right? And these were the chains. And you can see that really none of the chains is perfect, but in particular, this chain, which was the standard deviation of the beta, is definitely not a hairy caterpillar, right? It's definitely exploring the posterior space in different ways, right? So as the blue chain starts in whatever place, right, it has a hard time moving away from that. It's just giving very correlated on a step-by-step results, which are not the same that the other chain is giving. That the same problem is there also for the other chain, though we can see that it's slightly less correlated on a step-by-step base. And that might explain why we were getting 2 chains that were exploring at different tempos. The one that's less correlated was probably the faster one. The one that was more correlated, it's the slowest one. Good. So we found a problem with the fact that the sampler, the Queen Mobile, is not really able to explore the posterior space in an efficient way. There's something wrong there. And we're not sure that we would get exactly the same results if we were only to look at the posteriors from one chain and the posterior from the other chain. We then looked at the prior posterior update plots, and the update seems fine, but when we overlay the true parameter values from our simulation, we see that they're quite off, right? The mean bias was supposed to be 0, but the model is very certain it's something above 0. The true variance of the bias at the population level was supposed to be 0.1, if I remember correctly, and the model is very sure it's 0.3. The mean beta was supposed to be, again, I don't remember, something like point something, 0.3, let's say. But sorry, it was supposed to be 1.8. But the model is very sure it's 0.3. And the variance of the beta, again, is underestimating the variance, right? So it's not really good at recovering the parameters. It's not just that it's inefficient in exploring the posterior space, it's not even able to reconstruct the true parameter value, right? If it was only inefficiency, it was finding the right values, it was just taking a long time, that wouldn't be a problem, right? We could increase the number of iterations and so on and so forth, could wait longer, we could use the uCloud, but that's not what's happening here, right? So energy is messed up, though there are no divergences, which tells us that the funnel structures, so the structures according to which some regions of the posterior space can be well explored with steps of a certain size, and others should actually be better explored with small steps, are multidimensional, more than 2 dimensions. That's what the energy is telling us. Divergences tend to crop up when you have funnels that are 2 dimensions, and EBFMI tends to crop up when you have funnels that are only visible on larger dimensions. The chains are not hairy caterpillars. The posterior space exploration is messed up, right, as we suspected from the energy. And the parameter recovery is messed up. At the same time, the prior posterior updates actually wouldn't have given us an issue, right? And that's also to strengthen the idea that none of these tests will tell you whether the model has gone right on its own. You need to look at the whole picture. So the first thing that we could do once we look at those prior posterior updates that are not capturing the true values could be, oh, maybe we should just change the priors. Right? And in this case, I can tell you that no matter how you change the priors, it's not gonna work. The second step that we might do, right, is we might fiddle with the hyperparameter that tell Stan how to learn to explore this posterior space, right? We could tell it, well, we know it's going to be slower, but please change your delta value. That is basically you're learning from the initial exploration phase how you should adjust your steps. The higher the delta, that goes on a scale from 0 to 1, the higher the delta, the more it's gonna learn from each step and adjust and try and adjust again and try and adjust again and try. The lower it is, the more it's gonna have the equivalent of a low learning rate, which is it's not gonna learn at every step how to change much. It's gonna want to see a lot of evidence for decreasing the step size or for increasing the amount of steps that it needs to do. We can fiddle with the max pre-depth, which is how careful it is in not making U-turns, basically. We can change the amount of iterations. We could set it up to 100,000. All of these things will not solve the problem. Well, actually, do not, if you run it, do not solve this problem. So, yes? With these data. With these data. So, generally, those are the two things that I always do when I get problems. They rarely works, but they're the easiest one because you just change a number and then you let it rerun and go on with your life until that is done, right? What is going on is that actually we need to change the topology of the posterior space. That is, we need to change the way that the posterior is organized. We need to do what's called reparametrization. Yes?
Normally, say you're navigating this 2D space, right?
Normally,
Like if you explore 2D space,
yes.
and you're going along one axis, you look at the gradient, you know which direction to go.
Yeah.
When you have a multi-dimensional space, you have more directions to choose from, and that's part of the problem, right? So what's the default behavior when you're looking at a direction? Is it just follow the momentum and wherever it started? Or is it already guided for the specific direction?
Okay, so let's say that we are in a 300 dimensional space,
Yeah.
whatever. What we do is what the algorithm has to do is to actually look around across all the 300 dimensions, right? And says, if I do a step, because it's not like the x's are privileged directions. It's simply saying, if I go in this direction, so changing all the parameter values along these vectors, right? So imagine a small arrow in space, right? And then here is what the gradient is. If I go in that vector, right, then this is the gradient. In that vector, that's the gradient, right? And then it gets in this three-dimensional space, right, the gradient across all the dimensions, right? I don't know if I need to, did I bring my marker? Yes. So if we are in a three-dimensional space, which is the highest I can represent, you're gonna have that all of the dimension should, all of the possible direction in this possible space, including the one poking out of the white table, should be explored. And that's why it might take a long time to fit these very complex models, because it has to sample the gradient in this case, it would be a three-dimensional space. In a realistic model, it might easily go up to a few thousand parameters. And so what we need to do, the metaphor is basically stretch the space as if it was an elastic space in order to change the shape of the posterior, right? If you have a posterior that is like this, right? Imagine stretching the space here so that you can actually explore it with the same step size and amount of steps. It's weird because it's partly a metaphor, but it's also how the algorithm is working. So it's
So there's no privileged access, but at the same time, there is sensitivity to whichever ones you started to explore first. And also, when there are certain spaces that are narrower, more difficult to explore evenly, you want to try to give them a bit of an advantage by reparameterizing. It's easier to.
so there's sensitivity to where you start, and that's why we have at least two chains all the time.
Yeah.
Yeah. And if this is the space, right? If it's a funnel, and you're at the cusp here, and you look up, you feel like there's going to be a big change in the probability, right? Mm-hmm. It's probably, I don't know, it's going to increase your odds. Actually, very close to the cusp, and you look towards the cusp. If you go even one small step in that direction, the posterior probability is going to increase a lot. But since the algorithm is doing steps, it's not exploring continuously. It does a step, it expects that now it should be very, very likely given the data and the prior, and actually it's very, very unlikely. And then it says, well, then I've broken the physics of the simulation, right? I was expecting my kinetic energy to decrease because I'm going up, and my potential energy to increase because I'm going up, right? I'm going slower, but if I go down again, I'm gonna retake my kinetic energy. But actually, my kinetic energy, my potential energy after the step is much lower than I expected. There's something that has gone wrong, divergence. And that means that we cannot really explore the narrow area of the funnel because every time we make a step, we break the physics of the simulation. And that's where stretching it. I'm very tempted to go special relativity and talk about gravity, but the metaphor doesn't really work, so I shouldn't. We just want to stretch it here, right? We want to change the shape of the space underlying. We need to mathematically transform the parameter space so that the sampler can better explore it. And you actually done it already. So when you were doing, I think it's in methods 2, but maybe things have changed. Sometimes your models were not converging. And you were told, oh, it's because, well, one of your predictors is age in months of the children, and it goes from 0 to 90. And the other is their normalized score in whatever, linguistic ability compared to their age, and it goes from -2 to 2. And the model, the algorithm having to sample in that case, to estimate the maximum likelihood in a space that has x's that have very different scales, might be struggling to find the optimal solution. So a good suggestion is try to z-score the variables to put them all on the same axis. You remember z-score, you subtract the mean, you divide by the standard deviation. Everything is roughly between a scale between -3 and 3, if things were normally distributed. And then suddenly the model has an easier way finding the right solution, and you have an easier way comparing the coefficients in terms of the strength of the relationship conditional on the other parameters, blah, 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 right? Did you do this? Did you z-score variables at any point in your life? Good. The practical impact of that is actually you change the topology. of the underlying parameter space. Here, memory is already on a good scale, right? We have log odds that are roughly between -3 and 3. So we need to go deeper. Right? Instead of z-scoring the variables, we're going to z-score the parameters. So there's lots of info more on the Stan handbook. But the idea is that Stan really likes to sample from simple distributions. Yes?
Really, but when you say change the topology,
Yes.
you mean we can stretch it, right?
Yes.
But we can make something that was a ball into a donut.
You'd be surprised. Yes, sometimes we can. Because you can do nonlinear transformations. So what we've done also already by putting things on a logout scale can change the shape of the parameters space quite drastically.
Yeah, so the shape change, it's just we talk topology.
Yes.
We say that you are allowed to stretch as much as you want, but the topological features will still be the same. Exactly, demonstration.
Yeah. So yeah, you could say that the relative position, so if A is smaller than B and B is smaller than C, that relationship will stay unchanged in the underlying space, right? What we can do is we can apply like absolute transformations, and that wouldn't preserve those properties. It's really just any mathematical transformation, but you're right, we will not always change the topological properties of the space. Yes, but we can do that. Okay, so Stan likes to sample from very simple distribution. Its favorite distribution to sample from, it's a normal distribution with a mean of 0 and the standard deviation of 1. It makes Stan very happy to be able to do that. Right? Thank you, Stan. Like, when do we have to do that? So we had our distribution for the bias for an individual was a normal distribution with a mean of bias M and a standard deviation of bias SD, where bias M and bias SD are the parameter at the population level. We want to transform it into some sort of function of normal 0 and 1. And so what we can do very easily is we can extract the bias M, right, from the normal distribution, right? We're basically subtracting the mean like we were doing in z-scoring. We're saying that there's bias M plus a normal distribution with a mean of 0. Does that make sense? And the bias of bias SD, and the standard deviation of bias SD. And then we can extract the bias SD simply by saying that there's a normal distribution with a mean of 0 that we derived before, standard deviation of 1, and then it's going to be multiplied by bias SD. Right? Really basic algebra. Does that make sense? Are you all agreeing that these bias M plus normal 0, 1 times bias SD is the same as normal bias M bias SD? Good. And again, if you remember, we subtract the mean, we divide by the standard deviation. It's exactly like z-scoring your predictors. Centering and scaling. Yes. So in the Stan code, what we had was that we had a bias agent, right? And a beta agent. But we want to implement that change. So what we say is that now instead of a bias agent per se, we have bias M plus, I'm just gonna off, plus a bias individual deviation for the agent, right? The difference between the agent and the population level. And for the beta is the same. Right? The operation is simple, but I know it can be confusing. So that's why I'm going slow and I want questions if you have doubts. We're simply taking out the means across the participants. Then if we want to standardize, right? What we can say is that bias ID, not standardize or scale, or standardize, yes, is that it's really a bias ID Z score times bias SD. I'm just saying that this bias ID that it's here, it's actually multiplying something, the normal 0, 1, by the bias SD. Right? It's the equivalent of saying we have an individual deviation, which is on whatever scale, and we divide it by the standard deviation. And then when we need to generate the bias ID Z, we're going to say that it's just a normal distribution with a mean of 0 and a standard deviation of 1, which for unfathomable reasons for me is actually being implemented in a different way, different and faster way in STAN, which is standard normal distribution. And you don't specify the 0 and 1. You can use the 0 and 1 as just slower than this. And I should go and check what the C++ is for that and why the heck they did that. But apparently, since Stan really likes that, it's a good idea to make it really fast. And they made a faster version of the function. Both versions work. Both versions are good for the portfolio assignment. Just you know that there is a faster way. Then we need to go and code, right? So in the parameters, we have bias M, bias SD, beta M, beta SD. But now instead of having a vector of bias and a vector of betas, we have a vector of length as many agents as there are of bias ID underscore Z, which is our 0 to 1 little component that Stan loves, right? And the same for beta, a vector of length agents of beta individual deviations, rescaled, Z scored. Then we have our transform parameters, which have the memory as before, but also now have a vector of length agents called bias individual deviation, and a vector of length agents called beta individual deviation. We do the memory thing just like before, and then we say that bias individual deviation is equal to bias ID Z score times the standard deviation. The same for beta. Then we need to fit the model. And you can see the population level priors are still the same. But now we have that the bias IDZ and the beta IDZ, instead of being sampled from a distribution that has a mean of bias M or beta M and a standard deviation of bias SD and beta SD, is actually sampled from a standard normal distribution. And in the model, we say that the bias ID, bias individual deviation, is a deviation from the mean of the population. And the same for beta. Does that make sense? It's weird, right? It's one of those things that's super simple, like algebraically, but if you have to do it yourself, it takes a while to enter that logic. Yes.
Are you saying?
From a 0 to 1. Yes. From the same distribution, but now that distribution is not a normal with a bias mean, bias standard deviation. It's actually as a mean of 0 and the standard deviation of 1. Before we had this result, right? And now we get both chains finished successfully. The mean chain execution time was 749.5, which is 400 milliseconds faster. 400 seconds faster, sorry. And the total execution time is 754, right? That's very close to the mean, meaning that the two chains took approximately the same time. Good science, right? We do the diagnose. It says sampler transition, tree depth. We were always able to avoid U-turns. Checking sampler transition for divergences. We never broke the physics of the model. Checking the energy was good. There weren't high dimensional funnels. We checked the effective sample size, the autocorrelation between successive samples, all good. We check whether the two chains cover the same region of the posterior, all good. Processing was complete, no problems detected. So these has worked, yes.
We did in the reinforcement learning example.
Yes.
Where instead of sampling tau prior, which is difficult because it's bounded by 0.
Yes.
We took the log of it to get a normal distribution.
Yes.
Isn't that also reparameterization, or is that transformation? Because we don't.
So it is a specific parametrization of a truncated distribution, right?
Yeah.
I would hesitate to call it reparameterization only in the sense that I had started with the idea of a normal distribution, which wasn't truncated, and that's wrong. But if you tell me, okay, we could do it exponential, like an exponential of 1, which would mean that it starts very high at 0 and then it has a long tail. Or we could do the truncated normal. That is a reparameterization, yes. Right, you can conceptualize the prior as an exponential, which by default starts at 0. Or you can conceptualize it as a truncated normal distribution, which would be something like this. Those two are two different parameterization of the same prior, right? So it is a reparameterization. Yes. Does that make sense?
So what did that say about tau example with taking a lot of tau? Is that
That's also reparameterization.
Yeah.
Well, so yes, it's in order to respect certain constraints that we have, right? But it is a way of changing the parameter so it fits within those constraints. Yes.
Yeah.
So any mathematical transformation can be considered a reparameterization. Some are more prototypical than others, right? Yeah. The annoying thing about reparameterization is that it's a general property, but every time that you Google it, they always give you the same one example. Yes. But now I let you dwell in your satisfaction for a reparameterization well done. We still need to check our model. Don't trust automated checks, right? The chains are working, right? The divergences are working. We check our prior posterior updates. The model is learning, but then we check whether we're getting the right parameter values. Bias has gotten a lot better, right? Variance of bias? Not really. Variance of beta? Better, not ideal, right? The estimate, the true value of the parameter is on the tail of the posterior estimate. Mean beta? Not really. So you could play with the priors. You could do a full parameter recovery. You'd still not get optimal fit. And Ingve knows why, because he brought it up two lectures ago. It's because given that we're having the model playing against a random bias agent, which plays right. I can remember if 70 or 80% of the time, something like that. The bias and the beta are doing some of the same work. You can change the bias and not change the beta, and you get the same result. Or you can shift them in opposite direction and you get the same result. Right? So we can play with the priors and solve part of the problem. For instance, putting very tight priors around bias, making the strong assumption that bias is not what's driving the effects. Or we can redesign our experiment and saying, actually, the agent is not just playing against this random bias agent. It might be playing with an agent that changes bias over time, or it might midway through the experiment shift against a different agent. Does that make sense? This is really here to tell you, even if the model has converged, has no divergences, blah, 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 you still got to do your legwork and understand the model. Good. So reparametrization, and again, I had a lot of fun with Designer. What is reparametrization? It's an attempt at changing the shape of the posterior space so that we can effectively sample it. It's an old friend because we've done things that look like reparametrization, lack of convergence, try z-scoring your predictors, reaction times are only positive, try log transforming them. Right. The outcome is a count, try using a Poisson distribution as a likelihood and a log-link function instead of a normal. The outcome is a rate between 0 and 1. Well, you can use an inverse logit or a beta distribution. Right? You're always changing the space. Actually, beta distributions can be parameterized in two ways. I think Josh might have mentioned, right? You can have the amount of positives versus the amount of negatives. That's the alpha beta parameterization. Or you can have the something that roughly corresponds to a mean and the variance. And I always forget what they're called, the phi and the something, the rate. I can't remember what the rate is. Which are also ways of changing the underlying shape of the parameters. And in general, reparameterization is a creative mathematical process which a priori implements some of the knowledge that we have into the model, right? For instance, putting hard boundaries in a ways that are not hard boundaries for the sampler. And it's something that cannot be thought a priori, right? As you're fitting your model and exploring the way that it works, it's a procedure that might force you to adjust the model as you proceed. And that's the right thing to do, right? Again, I think I'm making these points because you have been taught, rightly so, and there is kind of a zeitgeist in the academic discourse these days that we should be more rigorous, right? And pre-register our studies and publish our code even before we run the analysis. And all of this is good as a tool to structure your work and not sort of parachute you in the middle of data and try a million different things without having thought it through, or running an expensive experiment without having thought it through properly. On the other hand, it has a tendency to assume a normative value, right? The only right analysis is the one that you pre-register. And that's bullshit. Because we don't know everything before, right? No matter whether you pre-register, and that's a real case with me as a reviewer, right? No matter whether you pre-register that age of the children you're testing is a random effect, meaning each age might have a different effect of the treatment or experimental manipulation, that's just wrong, because we expect changes of the effect through age to have some sort of continuity, right? If you, from 4 to 5 months, increase in the effect, we might expect that from 5 to 6 months, it will increase even more, right? It won't be completely uncorrelated. And so if that is the right analysis, modeling age as some sort of linear or monotonic or Gaussian process with a specific function depending on your theory, instead of that as a random effect, no matter whether you pre-register. This is not p-hacking. It's just listening and being self-reflective as you're modeling. I think that's okay. Lots of people are frustrated on the reparameterization. There's a bit of a discussion that I try to start every year on Twitter that you can check there, with people bringing their favorite examples of reparameterization. And generally, really the best way of doing reparameterization is having a model that doesn't work, documenting your process with a reproducible example, and posting it on the Stand forum, because people are really good at helping you solving stuff there. Modeling is hard, and usually I had a song from a cartoon, which is titled "Make Failure Your Best Friend," but YouTube keeps censoring my videos because it has copyright, so I'm not doing it now. And with that, oh yeah, just before we go on a break, what would be next in our multi-level model? We would need to add the possibility for the individual deviations on bias and individual deviation on beta to be correlated, right? People who tend to just, chimpanzees who tend to always pick the right hand will by default also have a very low effective memory, right? Chimpanzees that have low preference for right and left might have a bigger effect of memory, right? There's more space for variation there. And if we allow the two parameters to be correlated, the model is actually going to do even more effective partial pooling. It's going to be able to share information not only across participants, but also within participant across the parameters. And that's implemented in the course notes. And of course, then you would need to do a parameter recovery of the multi-level model. Yes, so multi-level modeling is a way of modeling sources of variation in the parameters, and is a way of partially pooling information, as we've discussed before, and brings challenges. There is more choices, which parameters vary, are variations correlated. It brings challenges to the model in converging, so we often need to reparameterize, and these z-scoring of the parameters is really a standard way of reparameterizing your multi-level models, to the point that most people really start by coding it that way. There's more parameters to recover, and there's the worry that some fields have, and we might face in some studies, as to whether we are missing some of the genuine individual variability by doing partial pooling, right? By dragging the individuals towards the population mean. We've discussed very briefly, well, if we have groups in our population, we might do the partial pooling only within those groups, right? Between participants with schizophrenia and other participants with schizophrenia, and between controls and other controls, but not across. And in any case, we need to visualize what's happening. There's additional examples on this specific issue in the online course that is in the Prep Your Brain part of Brightspace, if you're interested in seeing how this is done in practice. And then after the break, we'll tackle model comparison. Okay. So, what is model comparison? Anybody wants to? Why are we even caring? Yes.
I guess if we have recorded some data from humans or something like that,
Yes.
maybe we want to compare and see which of the models that sort of best describe the behavior that we see.
Yes, okay, exactly. So we don't have access to the true underlying data generating mechanism. We have some guesses, more or less motivated, some models. We want to know which of these models is most likely to be, if not the true one, but a better one than the others. And here, what is good enough and what is better is kind of playing into the big debates about data science and statistics in our time, which is, what does it mean good enough? What does it mean that it's able to predict data that it hasn't seen? Or does it mean that it's the true model, right? Consistent with the actual causal production of these data to the point that we could go and manipulate the mechanism and see the predicted change, right? Causal inference versus machine learning. Does that make sense? Okay, so given the model, the data, and more than one model, which of these models seems to describe or predict the data better and or with the least parameters, right? Does that sound familiar? That's kind of the problem that you deal in a lot of statistical modeling and machine learning modeling. If we can assume that these are the only possible models, and one of them is true, and that the data are fully representative of the population of interest, we can use model comparison to estimate the probability that each model is true. Okay, so in the Bayesian world, I guess there are a million, as in every word, a million different approaches, but two that are really dominant or that are more consistent with the theory. They should have appeared one at a time. The first one is an internal predictive performance of the model. Are you familiar with internal versus external validation? I'll touch upon that, so don't worry. But basically, internal means that you're taking a part of your data set, you're keeping it aside, and then you test the predictions of the model that has been trained on the rest of the data. An external validation might say, wait a minute, all these data come from CogSci students. What if we went down to Casino Bar and tested the truck drivers on a Thursday night? I don't know if it's open, but right? Would the model still be able to predict a slightly different population? This might seem, silly, but this is actually very relevant when you work with hospital data, because different hospitals tend to serve slightly different slices of the population. And so the validity of your model might have a great internal validity and a crap external validity, right? You might need to trade off between those two. We'll be talking about the notion of LU, leave one out, and ELPD, expected log probability predictive density. There should be two P's. There's no two P's. That really pisses me off, but it's only with one P. The second approach, we will not have the time to cover, but lucky you, there is a video lecture from the previous years exactly on that, which is basically within Stan telling that it could be these model or that model or that model. And the log posterior likelihood should be calculated as the sum of these three, of the probability of the first model times the first model, plus the probability of the second model times the second model, plus the probability of the third model times the third model. And by the way, the probabilities sum up to 1. Run the model and estimate. And that's a very smart way of doing that because you're really modeling everything in a consistent way. It takes forever to make it work. And that's why we're focusing on the very practical one. And then you can go and check the mixture stuff. There's both the video lecture and the course notes on that. So you can play with that. In any case, no matter the approach to model comparison that you want to adopt, we always apply our simulation-based approach to things, and we talk about model recovery. That is, we simulate data from each model. We fit each model on each data set and compare their predictive performance, or we fit the mixture model on each data set and compare the probability of each model. And then we ask, is the true data generating model in that specific data set correctly identified, and how strongly? Yes.
You also, I can't remember which lecture, but talked about internal validity in terms of parameter recovery. Is that ever something you also use when you compare models? So like, if one model can actually recover parameters that you know, but the other model can't, you can do that?
Yeah, this is an excellent question. Yeah. So I might need to think through a bit more if that's consistent, but the basic idea, the basic answer to that question is, if you have a model that doesn't recover the parameters well, it shouldn't even enter the model comparison, right? Because then it's really hard to compare it with the others because it's just not working very well. Of course, you will always have models that do not exactly recover the parameters, right? So then you might, write down, okay, there's different uncertainty in how well they recover the parameters. And when I do my overall evaluation, given the results of the model comparison and blah, right, that should also become part of your discussion.
So it's also internal validity just used earlier.
Yeah, so I think it's internal validity in the sense that it's before even seeing the data, right? And here it's more related to the specific samples or subpopulation that you are dealing with. Yeah. Okay, so let's take this one step at a time. So we do have a measure of model fit already in the model output. Do you know what I'm talking about? Right, we have the LP, right? The log posterior probability. The output of that target plus equal that we all adore, right? So for each combination of parameter values, so each parameter has a value, a dot in the posterior space. As we're exploring it, we calculate, given the priors, how likely is this value? Given the data, how likely is this value? And sum it up in log space, right? That's the target plus equal. So we get a measure of, given the data and the priors, how well these posterior combination of parameter values fits. This is our first measure. So I've remade all the slides this morning because in previous years I was going through the history of information criteria and it just doesn't fit this year. So that's what happens there. But what do you think are the issue of our log posterior probability if we want to use it as a measure of predictive performance of the model? Yes.
I was going to ask about it, but maybe you had to screen model
Because?
No. Just summing it up, just accumulate it. Maybe it would be higher if you have All parameters and all.
All the parameters go into the likelihood function, right? And so you're not summing parameter by parameter, but you're summing the combined impact of the parameters on generating the data, right? So it's really dependent on the data. So if your models are being fitted on different data sets, you cannot compare. But if they're fitted on the same data set, they can actually be compared. Good. Other issues or some potential issues? Well, so the first one is that its absolute value is absolutely meaningless, right? What does it mean to have an LP of 6286, right? We cannot really interpret it. So we cannot use it to see, is this model a good fit to the data? Yes?
Is it also maybe a problem that LP is log unnormalized probability?
Mm-hmm.
Um,
Because
is then the baselines between two models can be completely different. That was very poorly explained.
well,
that
so
means you can't compare them.
the idea is that it's unnormalized, and therefore we run the same amount of posterior samples in both models, and then we can use that to normalize it without having to calculate the integral. And if the two, but this is actually a good point. If the two models have a different number of posterior samples, that's a problem. But if we've done our work right and they have the same amount of post warm-up iterations, then that's not an issue. The next one is that we aggregate across all observations. And if you're entering this Bayesian mind frame, no, we never aggregate. We want all the information to be kept there. Right? We want to know for every observation, what's the log posterior probability of the model, because different data points, different participants, different subgroups, different conditions might be better or worse described by the model. Right? A model might be really good at describing how participants behave in one condition, but terrible at the other condition, right? So for instance, when we make people play against agents with increased theory of mind, models of moderate complexity, let's say reinforcement learning or one-level recursive reinforcement learning, thinking the other as a reinforcement learning machine, work very nicely. But if I put you playing against a 3-level recursion agent, you basically behave like chance. And a model with recursion would be really crappy at describing what you do. What we can do, and we will see how to do that in generated quantities, we can have the model generate the log post or generate and save the log posterior probability at an observation level. So we will have one value per sample, posterior sample, per observation, like big matrix. Yes.
Maybe this is a problem in like understanding the order of things that happens in staining.
Yes.
So if I have something that loops over the trials,
Yes.
so then the log posterior probability is sort of across all of those trials for all the participants, or how am I to understand?
Okay, yes, I think that's, yeah, I didn't explain that very well. So in the model, each iteration of the posterior space exploration, no matter how you coded it,
Yep.
will take all the data into account at the same time,
Okay,
right? It will say if we use this combination of parameter values, this learning rate and this tau, and we have this sequence of stimuli, how likely it is that the agent will produce a sequence of behaviors that is exactly like that of the participant.
okay,
Right? And it's not doing that, no matter even if you loop through trials,
mhm,
as you have to do in reinforcement learning, it will still take the probability of generating the full sequence.
okay.
Does that make sense?
And for also, if you also loop over agents, then it's for all agents
At the same time.
at the same time.
Right.
Okay,
So it will look around and it will say, given all the data in this direction, how much more likely or less likely does it become? In this direction, how much more or less likely it will become?
okay,
Because it has to fit all the data at the same time. In the generated quantities, you can actually say, well, actually take only one observation at a time, calculate the log posterior probability, and save it. Then move to the next trial, then move to the next trial, then move to the next agent, and save all of those. But the way that the sampler works, it takes all the data into account, which is the most efficient way of exploring the posterior space, because you don't want to go in a direction that fits some data, but not the other. Okay, then for those of you who do machine learning, it should be pretty obvious that the problem with log posterior probability is that it's training performance. So you're fitting the model on the data, and then you're asking how good is it at describing these data, which might work in some cases, but it tends to have issues like overfitting. Does that make sense? So how would test performance work in this context? Any idea? It's not obvious until you've thought of it, right? So yes.
I don't know if you do something like setting the posteriors for the parameters as like the true parameters to use, and then say, okay, given some new data, how likely are these posteriors?
Yes, so you fix the posterior space, right? Now you've estimated it. And then for each value in the distribution of posterior values, you say how likely are these values given, the prior and the data, the test data. So you take a multidimensional prior posterior of a model, multidimensional because you have more than one parameter, right? Simple reinforcement learning, learning rate, and tau, two-dimensional. You fix it, that's been estimated. And then for each sample, you say, given a test data set and prior, how likely is this combination of parameter values? Does that make sense conceptually? Good. Is there an issue with that? Okay, so for me, when I look at this, the issue is, of course, how do we define a test data set? That's a crucial aspect. The other, and that's problem coming from some areas of machine learning, is we still have a meaningless value. Right? The absolute value doesn't make any sense. If we use the measure of error on the true data, we might get something that's more meaningful for operationalization. The third one is that these models are pretty slow, And depending on how we define the data set, the test data set, we might, so if we do as I was anticipating before, a live one out, we might have a lot of models to fit. That's just a formalization of how this works. So these LP on external data sets, expected log pointwise predictive density are defined as 1 over n times the sum of the log of the probability of the set of parameters, model 1. Sorry, the probability of the data in the test set given the model fit on a data set that excludes the data on which we're testing. And usually in these kind of setups, we want to use some form of cross-validation, right? The idea is we have a limited sample size, and we want to be able to test the performance of the model on as broad a range of data as possible. So if we had 30 participants and we exclude 10 to do a test, the test is still going to be dissatisfactory. It's only 10, but also we removed a third of the data and our model is bound to perform worse because it doesn't have as much data to train. So a way of going beyond that has been the idea of cross-validation, where you divide your data set in n folds, right? You take one fold away, you train on the rest. Are you all familiar with this stuff? Good. So I'm going to go very fast, and you test on the remaining fold, and you repeat it for each of the folds. The more folds you get, the more accurate the prediction is going to be because there's more training. There's more representative training given the specific sample. But also, the more folds, the more dependent we are on how well the validation set, the fold, represents the heterogeneity of the population compared to the training set. What does it mean? It means, let's say that we're studying autism, which is a very heterogeneous population, where given the limited sample size in any realistic study, we will only cover a portion of the space. So let's say in an absolutely meaningless metric that the average distance of an autistic person sampled at random from the population, from our population, is 2. Now we look at our subsample. The more folds we do is at the extreme, leave one out. We only extract one participant. Our testing validity towards the full population will only stay if the distance between these participants that we left out is as big as the distance between the participants that we haven't tested and our subsample is. Given that there is always selection bias in the way that we build our sample sizes, samples in the lab, right? So if we are testing autistic individuals, right? And those are people who need to come to the lab, and we have advertised at university, we're going to cover a very specific population of autism, right? So there's going to be a big distance between the participants we haven't tested and the participants we have tested, which by doing a leave one out, we will likely underestimate. If we do a leave a chunk out, right, there's probably going to be a bit more difference between the chunk that we've extracted and the rest of the chunks, simply because there's going to be a lower likelihood that these chunks are covering the full sample that we have. Does that make sense? Good. So there is always a trade-off if the heterogeneity in the population that we want to study is high, we should be careful of increasing the number of folds too much. Pros, all data to train, all data to validate. Cons, it's low, more uncertain predictions because we have fewer data to train on. And we can worry about whether the sample is representative of new data compared to the ones that we already have. There's a couple of papers that some of your former colleagues have written to tackle exactly, to show the importance of these issues. And I just thought I would put them there. This is by Astrid, Emile, Marie, and Stine, where they were simply showing that you could build a very nicely working machine learning algorithms that identifies autistic individuals from the voice, which works very nicely in terms of task performance. And then you can simply ask the very same participants on which you trained to do a slightly different task, to retell a story instead of telling you what was going on in a video, and the performance of the algorithm collapses. Or another here is by Lasse Hansen, the first. We used to have a Lasse Hansen every year, where it shows that the model works very well in discriminating, let's say, autistic individual from neurotypical individuals. It's fantastic. And then you bring it into a real context where you actually have data from people with a variety of neurodevelopmental conditions, which is more representative of where these algorithms could in principle be used. And then it falls not to chance, but almost. Right? So, sorry to close that. In the way that ELPD is normally implemented, we have a crucial neglect of strata in the data so that it does a leave one out problem. And it relies on the internal validity instead of the external validity. So what we can do is we can actually combine ELPD with cross-validation. We create adequate folds. All the data from one participant only need to belong to one fold. We fit the model to all the folds but one, and we assess the likelihood of the validation data given the model, assuming a population distribution of the samples as in the training data set. So we can code it. The setup is the usual. We have one data set, two agents, a random and memory. We have therefore two models, a random and a memory. Will the memory models be better than random models on the memory agent? That's the question. Will the random models be better than the memory models on the random agent? That's really what we want to see. So we save observation-based log posterior probability in Stan in the generated quantities. Right, what we do is we say per each agent, per each trial, if we're doing the multi-level way, we create a variable called log_like, because that allows us to use a bunch of pre-made functions at a later stage. I would have called log posterior, but they call it log-like, which is a matrix, right, which we defined before. Do not forget to define log-like, which has columns for agents and rows for trials. And then we give it the Bernoulli logit log probability mass function, where that given choice is evaluated against a given theta. And if we don't want to use theta, we can unfold it completely, right? Bias at the population level for the memory model, plus the variation by individual, plus the beta population, plus the variation by individual times memory, right? Good. Then we want to calculate the expected log posterior probability if we hadn't seen that observation. And there is an estimated procedure, estimation procedure, which they called LU, just to make things confusing, which basically readjusts the probability of the different parameter values according to how frequent they would be in absence of this specific observation. But we don't really need to go into the detail, right? So we fit the models correctly to the correct data set. This is our model that we sampled, we fit it. It's the bias model applied to the bias data. And we call the method LU, which is pre-implemented. We give it 3 cores, so it's a bit faster. And then we want to save all the values. We do the same for the model that is biased agent applied to the memory data. And also for the memory data, memory agent applied to the bias data, memory agent applied to the memory data. And then we can start checking those values. So we can see here for each of the data points, what's the estimated log posterior probability given all the other data but that data point. Here we can see in the bias agent models when applied to the bias data and when applied to the memory data. And we have the same for the memory agent. And one of the things that we can see, for instance, is that there's fewer parameters, so the predictions are much more overlapping with each other. So it seems more sparse. Yeah, we're gonna skip that. Then we can look at how well they predict the data in a differential fashion. So we can subtract the one from the other. We can say if we subtract memory from biased, how is their difference in predictive performance on each data point gonna be? And what we get here is everything is centered at 0. So it's saying it's not very good at discriminating. On average, many of the data points can be equally described by the one model or by the other. Their predictive performance difference is 0. But we can see that the tail of the distribution, there are some data points which are much more, now I need to remember, this is the bias difference, ALTD. Okay, they're much more likely to be predicted by the biased. Bias minus memory, so negative values should mean that the memory is better, right? There are some data points that are more likely to be predicted by the memory, but on average, there is actually a slightly higher skew up here. When we look at the memory data, and now we subtract the memory from the biased, so we can see whether the right model is better, we can see that there is a very slight skew that you would need to quantify here to see, but all the tails are actually up there. So the memory model is much better for a few data points on the memory data set.
Is there an absolute interpretation of these EOPD values? Because on the left side, you have much lower values. So I was just wondering, because you said
This is differences, yeah. So there is no absolute.
Just because you said, there's some that are much better described by the memory model
compared to the rest.
Yeah, but it's 0.03, and on the other plot you have like values approaching 1.
Yeah,
so.
no, the absolute values have no meaning whatsoever. Okay. Yeah. But this is really hard to interpret. So what do we do is we can actually use a Lou compare, which is basically summarizing which one has the better predictive performance and how much worse is the other model and how much uncertainty there is in this difference. So here it's going to tell us that model 1 on the bias model on the bias data has the better performance, and 0 is the difference from the best model, and model 2 has a worse performance. How much worse? Minus 2.7. Who knows what that means, right? How uncertain is the difference? 0.5, which means that this difference doesn't overlap with 0 in its distribution. Right? If we look at the performance on the memory data, we see that model 2 is better. The memory model is better. The second model is the bias model, which is a minus 115, 116, with an even smaller standard error of the difference, right? This is about 1/10 of that. This is about 1/5 of that. So they are reliable. Whether they're meaningful, well, we need to do more evaluations, right? Yes?
Yes, we can very absolutely put the other minus 2.7 to the minus 116.
Given the number of data is the same, yes. And what we can say is that when you have random data, both models seems better at fitting them, relatively better. There is a smaller difference because when you have a memory model with a bias term, in principle, you could put memory at 0 and just use the bias term, and you can equally well describe the data, right? You will just be penalized a little because you have a more complex model, especially if your priors on the 2 parameters are broader, right? Because then that means you're going to add, maybe that relates to your question, you're going to add the target plus equal for the prior of bias, the target plus equal for the prior of beta, and the target plus equal for the likelihood function, right? Which means that models that have more parameters will be penalized, which is also something that we want because models with more parameters, they tend to be overfitting. We also have the side effect, and if your priors are very narrow, you're gonna be penalized as well, right? Because the different parameter values that are explored are going to be penalized, are going to be less likely given the very narrow priors. Okay, there's a rule of thumb on the Lou discourse that says that if the LPD difference is less than 4, the difference is small. If it is larger than 4, you then can compare it to the check whether it's reliable given its uncertainty. But I really hate these dichotomies, right? I'd rather go and say, well, how many times do we get it right with one model? How many times do we get it right with the other model? And then we can calculate. We can see whether it's accurate enough given our purpose. We can also do something smart. That is, sometimes the 2 models are capturing different aspects of the data generating process. So let's say that one of your models is a nice reinforcement learning, which captures the fact that the importance or the expected value might change as you play. And another is, I don't know, maybe not really updating the expected value, but it's making a model for the opponents that they're playing against. And therefore, they might be right at different times in the time series. So what we can look at is whether the difference in ELPD is consistent across all the data points, or if it switches across data points. And we can see if we were to average the prediction of the two models, what would be the optimal weight that we would give to the one model or to the other? Meaning, if my model is right 50% of the time and Clara's model is right a different 50% of the time, then the optimal weight would be a 0.5 on each model, right? We can create an ensemble of models that combines their predictions, and their predictions have a better performance than the prediction of each of the two models, right? This is what Lu model weights tries to estimate. It says, if we were to average the predictions of the two models, how much weight would be the optimal weight on each of the models to minimize the prediction error? And in this specific case, we say even if the difference in ELPD is very small when predicting the biased data, we really don't gain anything from the second best model. Right? It's wrong just where the other one is wrong as well. When we do the same on the memory data, we get again the same finding, but we're saying that all the weight should be put on the memory model, which is a really neat tool to have, because you can sort of, beyond just saying this is the better model, this is the worst model, you can actually say, do we gain more information by keeping the models together? Given that your models are also not guaranteed to perform equally well in all the tasks, in all the data set you try them out, that seems a safe bet. I think Richard McAreath equates these to a horse race that says, well, you do a horse race between 10 horses and one is the best. Are you going to shoot the 9 others? Or are you going to run additional horse races because different horses will win in different races, right? Okay, there is code. I'm not going to cover it in the detail, but it's explained in the course notes to actually then do this not at the individual observation level, but at a stratified level, right? So we can create a k-fold split of 10 folds with agents being put whole within folds so they don't split their data across folds. We create metrics to stuff in the log likelihoods that we calculate. We need to pass to the stand model both the normal data, but also the test data separately. We need to define the log likelihood in the generated quantities and the log likelihood tests. And we need to have not just the log likelihood as before, but also the log likelihood of the test. Then we can prep the data. There's things there. And then within the loop, right, within each fold, we prepare the data for the train. We prepare the data for the test. We fit the random model. We fit the memory model. And then we extract the log likelihood test. And then we can calculate the ELPD and the Lu compare and the model weights on this new parameter. And that's basically it. Yes. Good. So now you know model comparison. On Friday, what we're going to do is we're going to do a session of live coding where I will be applying the multi-level and the model comparison stuff to a reinforcement learning model, which I haven't prepared yet. But the idea would be, I don't know, we can compare one with unique learning rate against one that has 2 separate learning rate for positive and negative feedback. Good. Thanks for today.